Hello, welcome to problem solving session for linear algebra. I'm Siddhivalu Ambore from IIT Gandhinagar, and today we will discuss problems related to the topics from week 6 syllabus of week 6, and that is problem related to row operations, rank of a matrix, matrix inverses, and determinant. So we will start with our first problem, and so consider the following matrix. A is equal to 0 0 1 0 1 0 and 1 0 0, and we have to check the following statement to check following statements whether they are true or false. Okay, and the first statement is that the matrix A is in its row echelon form. We'll discuss the definition of row echelon form and others. So let me just write down all the statements. The matrix A is in its column echelon form, and third one is the matrix A is neither in its row echelon form nor in its column echelon form. Okay, so we have to check this for this given matrix A. So we'll start first with the definition of row echelon form. So we will go through definitions quickly before we answer this question. So first we'll see the definition of row echelon form. So recall that a matrix a matrix is in its row echelon form if each row is either 0 or begins with a 1. So if it has non-zero entry, it must start with 1. And once we have such 1, then below each such 1, there are only zeros. It means that all the entries below this 1 must be 0. So for example, if my matrix is of this form, so if the row is 0, so we are talking about row echelon form, so we will be checking the conditions over the rows. So if the row is 0, we don't care. Okay, so 0 row, we are fine with it. But if at all a row has any non-zero entry, then that non-zero entry must begin with 1. For example, I can't have this like 2 here, then 0 1, something like that. We don't need. So if a non-zero entry is starting, so we will check it from left to right, and the first non-zero entry of that row must be 1. So this will do. And once we have such 1, all the entries below this 1 should be 0. Okay, so once we have such 1, all the entries below this 1 should be 0. So I can have very well numbers here, but below this 1, so this is my leading one or the first non-zero entry of second row. Since it is 1, all the entries below that 1 must be 0. And so now this row, if I check the third row, it has this non-zero entry too. So if 0 is here, then this is not satisfying the condition for row echelon, because first non-zero entry for this third row is 2, but we are given that if it is in row echelon form, the first non-zero entry must be 1. So this either we can do is we can add 1 here, or we can make this 2 to be 1 or something like that. So, and similarly, once we have this leading one, all the entries below this should be 0. So note that this is also non-zero entry, but we don't care whether below this 2 is 0 or not. We can very well have 10 power some 100 or something like that. So, but once we have the first non-zero entry 1, below that 1, we must have all the entries 0. And that is the condition for row echelon form. So our given matrix is this matrix 0, 1. Our given matrix A is this 0 0 1 0 1 0, and it is 0 1 0 0. So we will be checking the first row. In first row, the first non-zero entry, so 0 0, and then first non-zero entry is 1. So, and all the entries below this 1 are 0. So this is 1, and all the entries below this 1 are 0. So that's why first row is satisfying the required condition. Now we will go on to the second row and we will check what is happening. So the first non-zero entry is this one, and below this one everything is 0. So we are fine with second row as well. Similarly, in third row, the first non-zero entry is 1 and there is nothing below this one. We don't need to check anything. So from this, what we can say, that this matrix A is in row echelon form. Okay. So this statement here, that this matrix is in row echelon form, is actually true. Okay. Now, second, they are asking whether the matrix A is in its column echelon form or not. So we will again go through the definition of column echelon form. Just a second. So this was first definition. A matrix is in its column echelon form if each column is 0 or begins with a 1, and for each such one there are only zeros to the right. Okay, so now in row echelon form, if we have leading 1, then below that 1 all the entries must be 0. Now in the column echelon form, so this was row echelon form, where the entries below the leading 1 are 0, and for the column echelon form, it is to the right of that first non-zero one must be 0. Okay, so for example, if I have a matrix of this form 0 0 0 0, sorry, we are working with columns. So first column, if it is 0, we are okay. Okay, the column is 0, we don't need to check anything. But if at all a column is starting with some non-zero entry, so for example, here it is non-zero, then I don't care what is below this one, but the first everything to the right of this one must be 0, something of this kind. Okay, and now I'm going to third row, third column. So if I have 1 here, then everything on its right must be 0, and here I don't really bother what the entries are. And again, from now here I can't, so I can, so these two rows are fixed. These first two entries of these two rows are fixed because of the leading one here and here. So I can choose among this, and I can have here 1, and then here it becomes 0, and here maybe 0 and 1, something like that. So this matrix is in column echelon form. Okay, so the first non-zero entry must be 1 in the column when I go from top to bottom, and everything on the right of that one must be 0. These two are the only conditions which we need to follow. And if the row or column is 0, then we do not need to check anything for them to be row echelon or column echelon form. So our given matrix was this matrix. So given matrix A was this. A is 0, 0, 1, 0, 1, 0, and 1, 0, 0. So I will check my first column. In first column, the first non-zero entry is here, this one, and everything to the right of this one is 0. So I am fine. Now I'll check for the second row. I will go from top to bottom. The first non-zero entry is this one, and everything to its right is 0. So I am fine. Similarly with third, and there is nothing to the right of this one, then we do not need to check anything. So this is also, this matrix is in column echelon form. Okay, so they were asking whether this matrix A in its column echelon form or not. So the statement is true. And now they are asking us the third question, that matrix A is neither in its row echelon form or nor in its column echelon form. Okay, so this is definitely not true, because we just saw that this matrix A is in both row echelon and column echelon form. So this last statement which they are asking is anyway false. Okay, so any doubt here in the definition of row echelon, column echelon form, or any such things? If you have any doubt, please unmute yourself and ask, or if you don't want to speak up, please write it in the chat and I will try to sort those doubts out. Any doubt in the definition? Yes,
The
sir.
example that you gave for column echelon,
Yes, sir.
not column echelon, right?
Is not column echelon. Why is it not column echelon?
No, the example I am asking. In the last row, you have,
This
yes. The
the
last
last
row,
row. Yes. This one or this
this
one? This first one or second one?
one, yeah, the red color one, yes, that one. First one.
This first one, okay.
It's not column echelon.
Why, sir?
Because the last row you have the third element 1 already.
Here, this?
Then again, followed by that, it's not all 0. So
Yes,
can
sir.
we
But
say?
this 0, this one is not my first one in the column. This is any one. This is not the required one. So what we need is, we only care about this one. So let me mark this. This is my first entry. So each column is non-zero and begins with 1. So column must begin with 1. And once I have such one, which is the beginning of my column, then all the entries to that one must be 0. So the only elements which are beginning ones are these ones. Okay, so and everything to the right of this is 0. I don't care here, this one, because this one is not something which I'm caring, because this is not my first one of the column. Is it clear? I mean, we are not checking all the ones anywhere in the matrix. Okay, so instead of this 2, 3, I can very well have this 1, 1, 1, and this matrix is still column echelon, because I only care about this square ones and not this triangle or any other. So when I start with, also when I start to check any matrix, the first non-zero entry must be 1, and I only care about what is to the right of this first one. And I don't care anything about the below entries or what is to the right of those entries. Is it clear?
Yeah, clear.
Okay.
Thank you.
Okay. Okay, great. Any doubt in the, like, any such doubts? Please ask.
Ma'am, can you explain again the row echelon form and the column echelon form? What is the
Okay, so
definition?
definitions I will again go through. So what it says is that I have to start checking. So for in row echelon form, I need to check the rows. Okay, so what I do, I check the rows from left to right. If the row entirely is 0, I am okay. I don't need to check anything, because they are saying each row is either 0. So if the row is 0, I don't care. But if the row has any non-zero entry, then that first non-zero entry must be 1. Okay, so for example, if I check this row, the first non-zero, so this 0, 0, I don't need to check anything. But this is something which is non-zero. So the first entry of this non-zero row must be 1. If it is 2, then this is not row echelon. So the first entry must be 1. And once I have this 1, everything below this one only. So let me mark this also. This with red. Yeah. This. Okay, so my row is starting with this one. And once I have this one, everything below this one must be 0. I don't care what is here. I mean, if there was 1 here, maybe not this. General. Okay, I don't care what is below this one. If it is, sorry, this has to be non-zero. Just a second. So once I have this one, everything below that one must be 0.
Okay.
And that's it. First must be 1 and everything below that must be 0 and nothing else. I don't care about rest. So when I start with the second row, the first is 1 and then below this one it is 0 and then I can have anything here, maybe 304 and something like that. I don't care. But if I have 1, the leading one of the row, so this red kind of stuff, then below that it must be 0. Any doubts? Only two conditions I need to check. Whether the non-zero row is beginning with 1, and if it is beginning with 1, then below that everything must be 0. These are the three conditions I need to check. If the row is 0, okay. If the row is non-zero, first non-zero entry must be 1. And if that first non-zero entry is landing in some column, then every entry in that column below that one must be 0. Is it okay?
Yeah, is it okay now?
Yeah, it's
In
okay now.
this
Great.
in this example,
And the last one we have.
Last
Um,
entry, we can have anything because this row does not have lead. I mean,
See,
I can,
when
if
we go
if it is
into the
0,
third row,
when
then
we go,
0, 1, 0, and the rest all are not 0.
no. In the row, we don't need. I mean, row could have anything. So, for example, I can have very well this 1, 1, 2. And now, if I am having 0 here, then it's okay. But if I am having some non-zero element here, then it must be 1 because we are now working in this last row, the fourth row now. And here I
But
can have maybe,
when we take 1, 1, 2 in the last row, then when we go through the first one, 1, 0,
Mhm.
0, then 1 is also
Here
0.
this one,
Yeah.
but this is not leading one. This is not first one of my row.
Leading one will be the first
This one,
A1
these
one.
red ones are the only first ones. And
Okay.
below that, everything is 0, so I am okay. So I don't care what is happening here.
Yeah.
Okay?
Okay.
Okay. Is it cool? I mean, is it okay now? Is there any doubt here? I mean, and this also need not be 0. Okay. Here we can have 2, 3, 4, maybe 2, 3, 4, or anything. Because once I have leading one, below it, everything must be 0. And I'm going from left to right in the rows. I can have 2, 3, 4, and so on. Row, first entry, below it 0, rest, I don't care. Second row, I go and check on for the non-zero entry. Below everything is 0. Here I can have maybe anything, 75. Just first entry below it, everything must be 0. That is row echelon form. For the column echelon form, similar. If the entire column, I will check the column from top to bottom. If the column is entirely 0, I don't need to check anything. But if the column starts, has some non-zero entry, then that first non-zero entry from going from top to bottom must be 1. And once I have that one, right on the right of that one must be 0. And everything below that one, I don't really care what is happening in that column. But everything on the right of that one must be 0. That's the only condition. So now here it was 1 below and 0. Here it is 1 right and 0. This 0 and this right. Is it okay now?
Yeah, okay.
Okay. Please understand those conditions carefully because they are a bit confusing. And if you are doubt, please ask. So we'll move on for now to the next question. Now they're asking, consider the following matrix. A is equal to 1 0 2 1 0 0 0 0 0 1 0 0. This is my matrix. And again, I have to check these conditions. Let me just copy them. Okay, so we have to check these for conditions, whether they are true, false, or what it is. So given matrix A is there, we already know what is row echelon form and column echelon form. So I will just write here the matrix. It is 1 0 0 0, sorry, 1 1 0 0 0 0 1 and 2 0 0 0. Okay, so I will check for now column echelon form. Okay, so first question is row echelon. So let us start with checking row echelon form. So I will start with the first row. First row, first entry is 1. Okay, great. But when I
But
go and check the
rest
yes,
entries are
yes,
not 0.
yes, yes, yes. So below this leading one, the all the non-zero it must have all the entries 0. But here I have these 2, so it fails. So this is not a row echelon. It is not in a row echelon form. Okay. And now we will check for column echelon. It is again 1 1 0 0 0 1 0 0 0 1 and 2 0 0 0. And now is it a row column echelon matrix
It is
or
not
it
in.
is
It is not
yes,
in. Yeah.
because
Column
again the
echelon.
first column itself. Yes,
Yeah.
it is not
One
the
and
column
the
echelon.
rest are not zeros.
Yes, sir. So the first column is when we go and check, the first entry is 1, it is okay. But when I go to the right of this one, this is non-zero entry, which fails to satisfy the condition of column echelon form. So again, this is again not in a column echelon form. Okay. Is there any doubt
No, ma'am.
here? Okay, so others also, if you have any doubt, please write it in the chat or ask. So we saw that this matrix is not in its row echelon form, not in its column echelon form. That's why this final statement, which is saying that matrix A is neither in its row echelon form and column echelon form, is true, and this is happening. However, if you go and check this statement, so this matrix again, it was not in row echelon form and it was not in column echelon form. This matrix, sorry, this was in row echelon form and column echelon form. Again, this matrix also, once it is not a row echelon form, it is again not a column echelon form. Now check for the third matrix. So let me write this. So now we consider this matrix. So consider a matrix A 0 0 0 1 0 0 0 1 0 2 0 0 0 0 1 and 1 0 0 0 0 0 1. So this is my matrix and I have to check whether this is in row echelon form and column echelon form or not. So this has the same question asked, that we have to check these conditions of row echelon and column echelon form. Okay, so what is your guess here? Whether this matrix, also let me write this matrix again. A is 0 0 0 1 0 0 0 1 0 2, everything 1. Then meanwhile, please guess based on the written rows that whether this is in row echelon, column echelon, or it is in what form. Any guesses?
Yeah. First one.
Okay, so already we have one guess in the chat that it is not in row, but it is in column echelon form, as already said by Karthikeyan. So, which is true. Actually, it is in row. It is not in row echelon form, but it is in column echelon form, and we'll check. So we'll start checking for the rows. So first row is okay. 1 is there, and below that everything is 0. Second row is also fine. 1, and then below it everything is 0. Third row, we have 1 here, but
On the
below this
separate
one we
measurement.
have this non-zero entry 2. So that's
Yeah.
why this is not in a row echelon form. Okay, so not row echelon form. Okay, and now we have to check for columns. So again, we'll go for columns, and or let me keep this here. So for column, first column is okay, 1, and everything to its right is 0.
0.
Second column, first here, and everything to its right is 0. To its right is 0. Third
Yeah.
column, first non-zero is 1, every to its right is 0. Fourth column is also 1, to its right
And
is 0, and fifth column, we don't need to check anything
yeah,
because there is nothing on its right. So that's why this is in column echelon
column echelon form.
form. Okay, so this is true. And the last statement is now false because we have that this matrix is in column echelon form. So note that if a matrix is in row echelon form, it need not be in its column echelon form and vice versa. Okay, it's not that if a matrix is in row echelon form, it has to be in its column echelon form. Okay, so that one thing you can check properly. Yes. So any doubts here now for the definitions of row echelon and column echelon form, please let me know if you have any doubts.
No, ma'am, there is no doubt now.
So now we'll move to our next question, question 4, and it is like we have to check whether the following statements are true or false. So the first question they are asking is the sum of two elementary matrices is an elementary matrix or not. Okay, so this is what they are asking. So elementary matrices, if you remember, there are three types of elementary matrices. First one is, so elementary matrices are obtained by applying just one elementary row operation.
Yeah.
So that is the definition of elementary matrix. So there are three types of row operation. So there are three types of elementary matrices also. So the first type of, so type 1 elementary matrix is obtained by interchanging,
By interchanging rows.
yes, interchanging ith and jth row. Type 2 is by multiplying a non-zero scalar, multiplying a non-zero scalar. So it here non-zero is important, non-zero scalar to a row. And type 3 is obtained by a scalar multiple times ith row to to the jth row. So scalar multiple times ith row to a jth row. Okay. So these are three types of elementary matrices. So we are asked whether the sum of two elementary matrices is again a elementary matrix or not. So any guesses? Whether a sum of two elementary matrices will be elementary matrix or not? Yes. As we already have a guess in the chat that it need not be elementary matrix, and which is correct. So since we are saying that it need not be elementary matrix, so we have to give an example for this. So we can have plenty of examples, but just one which I would like to give here is, so if I have this elementary matrix E1 is this 0 1 0 1 0 0 0 0 1. So this is R3. This is what we are doing is this matrix is in M3R, and what we are doing is we are interchanging first and second row. Okay. And again we take this second matrix. Let me do this here. 1 0 0 0 1 0 and 0 5 1. So what I am doing is I am 5 times 5 into second row added to R3. Okay, so R3 is what? 5 times second row added to R3. So this is my second. So these are elementary matrices, only one operation applied. But when I add these two matrices, let me add these two. I will get what? E1 plus E2 is 1 1 0. I'm adding these two matrices, okay? 1 1 0, and here I have 0 5 and 2. Okay, so this is my matrix. And this is clearly not an elementary matrix. Okay, elementary matrix is obtained by only one row operation applied to identity matrix. And this is definitely not of that kind. So this is not an elementary matrix. Okay. Any doubts here? Because it's neither interchange nor one column multiplied, one row multiplied by a scalar, and non-zero multiple of another row added to some jth row. So this is not, so this statement is false, that the sum of two elementary matrices need not be elementary matrix. Okay, any doubts here?
This elementary matrix interchanging of this row is with respect to what? Can you elaborate?
With respect to means?
I do have E1 and E2. Can you please scroll down?
It's rows, right? Sorry, I couldn't hear you properly, sir.
Now, can you please scroll down slightly? That E1
Yes.
plus, yeah.
Yes.
So E1 plus E2, you have got some matrix. So how we are concluding that this particular matrix is not elementary?
The third one. So this is elementary.
Yeah,
Because
how
we
you
are,
are telling how it is told that E1 and E2 are elementary? Is
because
E1
it
how?
is, we did that. What we did, how elementary matrices are
Hello.
obtained. It is,
Anji sir.
hello. So it is obtained by applying one row operation to the identity matrix. Identity
Okay. So
matrix means
identity matrix is
yeah, this is.
yeah.
So when I apply only one, interchanging ith and jth row of identity matrix. So let me write identity matrix in identity matrix. Now is it clear? So when I
Yeah.
interchange these two row, I get this. Only one operation applied to identity matrix I3. Similarly here, what I'm doing is, this matrix I have, I'm just multiplying the second row by 5 and then adding it to the third one. So this is again also elementary matrix. But I cannot have such operation applied to this I3, which will give me this matrix. So this is elementary matrix, only one operation. This is also elementary matrix with one operation, but here it is not, because whatever I do, I can't have this matrix E1 plus E2 just by applying one elementary row transformation to identity matrix. Is it okay?
Yeah, it's okay. I just have a doubt that whether elementary matrix is always like here you are defining elementary matrix with respect to an identity matrix. So do we define elementary matrix always with respect to some matrix? Like
Not
how it
with
is there.
respect to some matrix. Elementary
So always
matrix
with
is only with respect to identity matrix. We can apply elementary row operations on any matrix, but the definition of elementary matrices is by default one row operation applied to the identity matrix. So elementary matrices are only this, because this I can always say that this matrix for any given, I can just produce some A for which this matrix is obtained by applying one row operation and so on. Okay, so or I can just, what I can do is I can write this 110 and 110, and I can just say that when I interchange first and third row, I am getting this matrix. So that's why this is elementary matrix. No, that is not what we are saying. So this is completely wrong. What I need to do is I need to have I have identity matrix and I apply one row transformation or one elementary row operation and get this matrix. Then I call it elementary matrix. Is it clear now?
Yeah.
Okay, great. Oh, so let me just, okay, I think that's okay. So this kind of thing is not there. We have to have element identity matrix to start with to conclude whether a matrix is elementary or not. Okay, so please understand that. Okay, so this statement is false. I think now it's clear. Okay, so now we have sum of two elementary matrix, and now the sum of them was not elementary matrix. And now second question is, an elementary matrix is an invertible matrix. Okay, so what is the guess? So given an elementary matrix, they are saying every elementary matrix, that is just one row operation applied to identity matrix, the resultant matrix is always invertible. So that is the question. And any guesses? Yes. Yes, so we have one guess which says that yes, this is true. So as Jackie said, this is true. So we will try to prove this, because they are saying that an elementary matrix is an invertible matrix. So they are talking about any given elementary matrix. So there are three types of elementary matrices. So we'll consider these three types, and we'll prove that for each type we can prove that this is invertible. Or okay, so there are two ways to prove that some matrix is invertible. And one of them is just find its inverse and show that it is identity matrix. And that's it. We can say that this is invertible matrix. Okay, so let us try that for type 1. So type 1 was interchanging ith row and jth row. Interchanging ith row and jth row. So suppose I denote it by Eij. So it is I with, not I with, obtained by ith and jth by interchanging ith and jth row of of the identity matrix. So understand that when I multiply a matrix by some elementary matrix, the resultant matrix, so pre-multiply. So for example, if I have some matrix A and if I multiply it by this elementary matrix Eij, what it does to this matrix, the resultant matrix is matrix obtained by, we get a matrix with obtained by interchanging ith and jth rows of A. Okay, so the resultant matrix is of this form. Okay, so if I want to produce a matrix such that when I multiply that matrix by Eij, I will again get Eij. I will get identity matrix. What can I do? So Eij is what? It is identity matrix 1 1 happening, and then suddenly we are changing some ith and this jth rows and something of this sort. So this is happening. But when I again, if I multiply, so this is my Eij. This is ith row, this is jth row, and this is my matrix Eij. So, but when I multiply this matrix Eij by Eij, what it will do it will again swap this ith and jth rows. And when I swap again back to this, I will get what? 1 1 1. Now jth row had this entry here, but it will now shift to 1. Everything. Now this one will shift down to 1 here and 1, and I will get this an identity matrix. So I can say that Eij into Eij is identity. So that's why Eij is invertible. Any doubts here? What I did was I just produced a matrix such that when I multiply that matrix to Eij, I will get an identity matrix. So how I did that? So Eij was just ith and jth row swap. But when I again multiply the same Eij, the same elementary matrix with the elementary matrix Eij now, it will swap the ith and jth row of this. So for example, if I call this Eij1 and Eij2, so when I multiply this Eij2 with Eij1, which was our original matrix, it will again swap the ith and jth rows. So the swapped ith and jth rows, when I swap again, they go back to their original places in identity matrix. So that's why we are getting identity matrix. Any doubts here what I'm saying? It is like we are swapping the two things twice and they are now going back to their original places in the identity matrix. Is it clear? Or is it confusing? Please, any inputs from your end? If you have doubt, please ask. Otherwise, I will assume that, okay, you understood and I will then move. So now I want to I need to check for type 2 matrix. So okay. So what we are doing is, okay, so if I have this, so E12, okay, in 3 cross 3. So it is what? 0 1 0 1 0 0 0 0 0. So 1 and 2 swapped. But then again E12 I multiplied by E12, it is what? 0 1 0 0 1 0 0 0 0 1. Again multiplied by 0 1 0 1. And when I multiply these two matrices, this is E12, what I will get is, just check that this first entry will be 1, rest will be 0. Second is 1 here, so 1, sorry. Second is here 0. Now this tooth entry will be 1, rest will be 0, and similarly here. Okay, so what I was saying is, if I have any matrix, so if I show this to you in 2 cross 2 form, what I will get is C, D, A, and B. So just rows swapped. But if I again multiply this matrix by again same matrix, I will get the resultant matrix will again swap the original matrices, then and it will give me ABCD again. So when I multiply twice, when I interchange I and J twice, it's like I'm going a cycle, 1 to 2 transposition, 1 to 2, 2 to 1 kind of stuff. And when I do that twice, I will get the identity kind of stuff. So that's what I'm doing here. Is it clear now with 3 cross 3 matrix? Okay. So now we'll do for type 2. So type 2 is what? Elementary matrix elementary matrix with ith row of identity matrix multiplied by some non-zero C. Okay. So what it is of this form, if I am multiplying, so it is 1, 0, 0, and so on, 0, 1, 0, and so on, and some C row, some ith row, I have 0, 0, 0, and this C, 0 again, and rest are just 1, 1, and so on, like identity matrix. So it is only ith entry of the diagonal. If I go on checking diagonal, everything is 1, except for that ith row. Instead of 1, there is C. So what I want to do is I want to find inverse of this matrix. So what can I do? I need a matrix such that when I multiply that to this matrix, I will get back 1. So what I'm saying is, if I have 3 cross 3 matrix, 1, 0, 0, 0, C, 0, 0, 0, 1, and if I multiply, I need something so that when I multiply it, it will give me identity matrix 1, 0, 0, 0, 1, 0, 0, 0. Note that C is non-zero. So we can make use of that. Okay, so the best thing to do is, so when I have
You
matrix A,
can
and
create,
yes, sir,
can have an inverse matrix with 1 by C as your.
exactly. We can
So
have
you'll,
inverse matrix
so
with
you
the
do that
I.
by using the identity matrix and then create a new elementary matrix.
Yes,
Yeah.
yes. So what we will do is we will produce a new elementary matrix with ith row multiplied, instead of C, I will multiply by 1 by C. Okay, and this will give me identity matrix. So similarly, so this E 1 by Ci into E Ci is identity matrix. Okay, and you can check that clearly, because what any idea elementary matrix of this form does, it multiplies the entire row by this scalar here. Okay, so here everything, so it is what doing, it is multiplying this C row. Everything was fine. Everything was 1, 0, 0, 0, 1, 0. Ith row, it was 0, 0, 0, C and 0 and so on. And what it is doing, it is multiplying this ith row by 1 by C. So zeros are fine, but this C into 1 by C will give me 1 here, and everything is now again like identity matrix. Is it okay? So this is identity matrix of order any n which you choose. Is it okay? I think it was okay because This was kind of easy compared to the previous one. Yes, okay, so it's clear. So now this is last part. This is a bit tricky. To understand, one thing I want to mention here before going to third, that this elementary transformation matrix or these elementary matrices which are obtained by doing that some operation R on identity matrix, and when I multiply this, so this operation R, E is elementary matrix obtained by some operation R done on identity matrix. So when I multiply this ER with A, what it does is it applies that operation R on matrix A. Okay, so please understand that. So if R is some interchanging of rows, it will interchange the ith and jth row of A. If I am multiplying, obtain this ER by multiplying it by some scalar to ith row, then it will multiply that same number to the ith row of matrix A. And similarly, it does for type 3. So if I am obtained this ER by multiplying some C multiple of ith row adding to jth, then it does same. It multiplies the, not multiplies, it takes C multiple of ith row of matrix A and add to the jth row of matrix A. So that's how these elementary matrices work. So, and that's what I'm doing here. When I'm applying this EIJ and so on to my original matrices, I'm doing the exact same thing. So for type 3 now, type 3 is scalar obtained by scalar multiple of ith row is added to jth row. So let me denote it by E Ci, comma j. So I'm multiplying I by C and adding it to the j. So it is again identity matrix, and now ith row is like that. Ith row is not changing. The jth row is changing. And what it is doing, so if ith row is of this form, so if this is ith row, then what it does is it multiplies C to this I and add it to the jth row. Everything 0 is as it is, 1 here as it is, and so on, and 1 and identity matrix stuff continues. It is of this form. So how to obtain the identity matrix from this? So what I want to do is I want to make this C0. And how can I make this C0? What I want is I want to add minus C to this C and I can make this 0. And how can I do that? I can apply, now I can take minus C multiple of ith row and add it to jth row. Then it will be C minus C and it will give me back 0. So if I want, let me do this. So if this is my matrix 0, 1, 0 and I am adding 2, suppose here. So if I do this, so this elementary matrix, what it does, it multiplies second row by 2 and add to the third row. And what this matrix does, it multiplies the matrix by minus 2 and gives me back and adds it to the third row and gives me the resultant matrix. So let me multiply this. This is 0, 0. Here everything is 0, 1, 0. And here it is, note that here it is 0, minus 2, plus 2. So here I have again this entry 0. First entry is anyway 0. Second entry is 0, minus 2 into 1, minus 2 into plus 1 into plus 2 is 0. And this last entry is 1. So is it okay now? Like that's how it is working. So for this ECIJ, what I need to do is E minus CI comma J, and this will give me the required identity matrix. Is it okay?
Is there a way to identify elementary matrix?
Is there a way to identify elementary matrices? Okay. I mean, there is way because there are only 3 type of elementary matrices. Okay. So first is if we know how identity matrix looks. So if there are only interchange of 2 rows, we can clearly guess that one. And if it is just diagonal entries with everything 1, just one of the entries not equal to 1 and non-zero, then it is then it is elementary matrix. And third is identity matrix added and some one of the zeros of identity matrix is replaced by some non-zero number. Those are the 3 types. So let me just write it down. First is interchange of
Actually,
identity.
I do this types 1, 2, and my doubt is like when there is a combination of such operation, like suppose
Then once we
there
have
are
combination of operation, then it's not elementary matrix, first of all. When we
okay.
have combination, it is no. Elementary matrix means 1 row operations. Once we have second row operation, it is no longer elementary matrix.
Okay.
Then it is
Okay,
some
thank you.
matrix which is obtained from applying elementary row operations to the identity matrix. That is okay. But elementary matrix is only 1 row operation applied to identity matrix. So we can easily guess that one. Either it will be swap of 2 rows, or it is multiplied one of the 1 on the diagonal by some non-zero scalar, or no, product of 2 elementary matrix need not be elementary matrix. For example, we have this product of 2 elementary matrices, but it is identity matrix. Identity matrix is not elementary matrix.
Okay, okay. Okay, I got it.
Okay. Ramya, is it okay? I mean, product of 2 elementary matrix need not be elementary matrix. No, I mean, these are the examples. Identity matrix is not elementary matrix. Is both elementary matrix are obtained by applying same operation. Okay, is both.
But multiplying 1 with identity matrix, whether it's identity matrix is not elementary matrix, you said. But if you multiply 1 with that, then how?
Okay, yeah, I mean, that can be considered, but I can show you an example where product of elementary matrix is not elementary matrix. I mean, we can just take this. Oops, sorry. And here, if I go, this is 0, right? I'm doing it correctly. 0. This is 1. This is 0. This is 2 here. 0 here. 0. And I think this will be 1. And this is not elementary matrix. Okay, this is non-trivial example. Is it okay?
Yes, yes.
Yes. Okay. And what, Sania, I couldn't understand your question. Could you please elaborate? Meanwhile, what Ramya said, that the inverse of an elementary matrix is an elementary matrix, it is true because we just saw this by these examples, that inverse of elementary matrices will be of exactly this kind. For EIJ, it will be the same matrix. For ECI, so if it is some non-zero scalar multiple to the row, we can take inverse of that scalar since the scalar is non-zero and multiply that row and the corresponding matrix of this sort. This is elementary matrix again. And for this also, minus C multiple of ith row added to the jth row will give me inverse to the matrix which is obtained by multiplying ith row by C and added to the jth row. That is the answer to the question Ramya asked. Okay, so inverse of an elementary matrix will always be a elementary matrix, and this is exactly what we did in this example. And Sanya, is both elementary matrices are obtained by applying the same operations or by different operations. So if different elementary matrices can be obtained by applying different elementary matrices, but in this case, these are same. Like to obtain the inverse of type 1, we could inverse of type 1. For similar to type 2, the inverse was of type 2. And inverse of type 3 matrix was again a type 3 matrix. If that was your question, I hope it is clear, Sania. If it is still not clear, please write down. I mean, that's what I understood from your question, so I'm answering accordingly. But this is clear, right? That this is true. Every
Ma'am, I
elementary
am asking that we in type 1 we have
in type.
taken two same elementary operations.
Yes.
If one elementary operation have the type 1 and other is type of 2, then they are invertible.
All elementary matrices are invertible. Even the product of elementary matrices is invertible.
Or and
But
ma'am,
product of elementary matrix is invertible, but product need not be elementary matrix.
okay ma'am, thank you.
Yeah. Is it clear, right? Product is invertible matrix. Every elementary matrix is invertible. Product of elementary matrices is invertible, but product of elementary matrix need not be elementary matrix. It will be invertible, but not elementary matrix.
Okay ma'am.
Elementary matrix is square. Yes, it will always be square because we are obtaining it by applying row operation to an identity matrix. So identity matrix is always square matrix. So that's why it will always be square matrix. Is it okay, Ramya? Okay. So we'll move to the next question, which is, so this was true. Okay. So every elementary matrix is invertible, is true. We just saw what kind of inverse they have. And now we are moving to third question. The inverse if exists, which we just proved that exists, of an elementary matrix is always a elementary matrix, and which is true. This is what I guess Ramya just asked me this question, that whether product of inverse of elementary matrix is elementary or not, is always an elementary matrix. Okay, this is true by just above what we did in earlier example. Okay, or question 2. Please let me know if this is not clear, that inverse of a elementary matrix is again elementary matrix. We just produced an elementary matrix which is inverse of given elementary matrix. Okay. Now they are asking whether the transpose of an elementary matrix is elementary matrix. And what is your guess? Transpose of an elementary matrix is elementary or not? First of all, note that type 1 elementary matrix is interchange of ith and jth row, right? And if I just write this here, example in 3 cross 3, it will be, what is transpose of this matrix? This is elementary matrix E1, 2. 1 and 2 are interchanged. Now let me write like this. What is transpose of this matrix? It is same matrix. So actually the transpose of any this type 1 elementary matrix is the same matrix, which is by default is an elementary matrix to start with. So that's why for type 1, this is true. The transpose of an elementary matrix is again a elementary matrix. Okay. Is there any doubt here to see whether the transpose of an elementary matrix is elementary or not? For type 1 at least. It will in fact, interchanged ones will be symmetric matrices. Symmetric means the transpose are equal. Similarly, for type 2, please ask if there is any doubt. Okay. Type 2 are scalar multiple, non-zero, scalar multiple, multiple of ith row. Or multiply, non-zero scalar multiplied to ith row. So it is of this type, right? 1, rest are zeros. So I am not writing zeros. See somewhere 1, 1 here. And I am taking transpose of this. So what it will be? Again, 1 and again 1 here. C, 1 and 1. It will be the same matrix. So if it was Ci, this will again be ECI. Okay, so this is again a symmetric matrix. And therefore, and it is same, its transpose is in fact again same elementary matrix. So that's why this statement is true for type 1 and type 2 elementary matrices. Now for the third type. Now third type, so let me write this for scalar multiple of ith row. Scalar multiple of ith row added to jth row. Okay, so let me write this for this explicit example of R3 in M3R. So let me take this 1, 0, 0 and 2, 0, 2, 1, 0, 0, 0, 1. So this is elementary matrix. It is E 2, 1, comma 2, 1, comma 2. So I'm multiplying first row by 2 and adding it to the second row. That's what I'm doing. So this is elementary matrix obtained by applying just one row operation to the identity matrix. And transpose of this is what? This matrix 1, 2, 0, 0, 1, 0, 0, 0. Oops. Yeah, 0, 0, 1. And what this is? Can somebody guess what this is? Whether this is elementary matrix or not? It is, right? Because what this is now 2 times 2 times second row added to the row 1. So if I have this ECI comma J, its transpose is in fact ECJ comma I. So what we are doing it now, we are multiplying second row by 2 and adding it to the first row. That is what happening here. Is it clear? Any doubts here? So this one is R1, 2R1 added to, let me write it. R2 is 2R1 added to R2, and this is R1, 2R2 added to R1. And when I'm doing this, I'm doing everything in identity matrix because we are talking about elementary matrices. Okay, so is it clear? I'm also writing explicit expression for all three type of elementary matrices. Okay, so what it will be? So for transpose of type 1 will be the same matrix. Similarly for type 2, but for type 3, we are changing it a bit. And if you understand this by previous notation, it is what this will be. Any doubts here to understand how it is happening or anything? First two are symmetry matrices, then transpose are the same matrices which were elementary. For third one, the expression changes a bit, but it remains a elementary matrix. So this statement which they were asking is in fact true. The transpose of an elementary matrix is again an elementary matrix. Now the question 5 is, fifth question in this true false, that if A and B are invertible matrices, let A and B to n cross n matrices, invertible matrices. Then they are saying that there exists a sequence of elementary matrices not elementary operation, elementary row operation which transforms A to B. So what they are saying, so when I apply any row operation, it is just like I am multiplying an elementary row operation, elementary matrix to that matrix A. Okay, so we'll talk this about this elementary row operation in terms of multiplication of elementary matrices. So note this theorem which is already given in your lecture series, that let A be an n cross n matrix, then A is invertible if and only if A can be written as a product of elementary matrices. So when I say this, what I mean is, when I apply finitely many linear operations on this matrix A, I end up getting identity matrix. That's what this statement means. So what they are saying is that if A and B are two invertible matrices, can I start with A and do elementary row operation and obtain B? It is similar to say that I'm starting with matrix A, I multiply that matrix A with sufficiently many suitable elementary matrices and I am obtaining B now. So that is what they are asking. And so what is your guess, that can we do this? Can we transform any invertible matrix to any other invertible matrix by just linear transformations or multiplication of elementary row matrices? Any guesses? Okay, so already we have one guess that it says that it is true. And as Jackie suggested, it is true. We will try to prove this, or we will try to give expression that how can we convert this A to B. So it is given that A is invertible, then I can write it in terms of product of elementary matrices, right? A inverse is I, B inverse is I. I mean, that is okay, that both of them have inverses, but they are saying that we are transforming them. So it is like I have A here, I apply row transformation, I get some matrices, and I end up getting B. This is what they are asking. So what we can do is, so we will use this theorem here. So what they are saying that since A is invertible, I can write A as A is actually what? Finitely many elementary row operations applied to identity matrix, right? And similarly, it is also given in your lecture, then that A inverse is just EK inverse, EK minus 1 inverse, so on, E1 inverse. Okay, okay, or let me write this as A1, A2, AK. So when I'm writing this as A1, A2, AK and AK, I mean they are all elementary matrices with suitable linear transformation, which is giving me A. And similarly, this statement here, which I'm writing here, is proved in the lecture, okay? Please note that. And even if it's not proved, you can clearly check that this is obtained by this fact that AB inverse is B inverse, A inverse, and so on. So it is quite clear. And similarly, since also B is invertible, what I can similarly write this, right? EB1, EB2, so on up to EBK. Okay. And this is my B. So what I will do is, I have A here. I apply this linear transformation of A inverse to A. And what I will get is EAK inverse, EAK minus 1 inverse, so on, and up to EA1 inverse. This is A inverse, right? So these two products will give me I. And I will multiply them by EB1, EB2, so on, EB, not K. Let me write some M. EBM. And this is matrix B, because A into this row operations will give me identity. And again, when I multiply them by these elementary matrices, or when I apply these row operations, I will get back my B. Not get back, but I will get B. Is it okay now? This A into A inverse is identity. So this is identity. Let me write here. This is identity. I mean, is it clear? Please, any doubts, or do I need to repeat this or anything?
I was referring to the same thing, but I was not able to specify it in the elementary form. That's why.
Okay. Okay.
So I was saying that because A inverse is equal to I, then we can use that relationship to
Yes, yes. I
get
mean,
to
what you did was exactly the same. When you wrote that A inverse and B inverse, you meant these elementary matrices by, I think.
yes, yes.
Yeah, exactly. So it is clear, right? So what we are doing is we are starting with A, and since this is invertible matrix, we can do finitely many elementary row operations, and we can have identity. And once I have identity, since B is invertible matrix again, I can have again this product of row operations such that I will get B. So I will just apply those again on that I to get B. So I am starting with A, and I am somehow getting identity in between because of these expressions. And then again, I go on multiplying them by elementary matrices to obtain B, and I will get B. So that's how it goes. Okay, so I hope this is clear. So this statement that I can start with the matrix and then I apply elementary row operations, and I can get any other invertible matrix. And this statement is true. If you have any doubts, please write it in the chat, or you can just ask by unmuting yourself. Okay, so we'll move to next question. Question 5 is compute the rank of following matrix A is equal to pi 1 0 Okay, so we have to compute rank of this matrix. A So you all know what is rank of a matrix, right? We know rank of matrix is just related to the rank of transformation which we learned. So what we do is, let me recall the definition that let A be an M cross N matrix, then LA is linear transformation from Rn to Rm, defined by L A of X is Ax. Okay, and so this is linear transformation, and we have explicitly proved, in fact, in our previous one of the previous classes, that this is linear transformation. We actually checked the condition of linear transformation, and we checked that this gives us linear transformation, and the rank. Then, if we have this linear transformation, we define the rank of matrix A to be rank of LA, rank of this linear transformation A. And we know that rank of linear transformation is rank of range space of this linear transformation. So what we have is that rank of we define the rank of A is rank of this element, this linear transformation LA. So this was the definition. I'm just going through definition. So any guesses?
Can you please explain on that LA?
Yeah.
What exactly?
Okay, what exactly it is? It is a linear transformation going from Rn to Rm, such that A is M cross N matrix. M cross N matrix, and LA is linear transformation from Rn to Rm, such that Rn is what? Rn, I can look at it as matrix N cross 1 going to some matrix M cross 1, right? So how I am doing this? I'm multiplying, I hope, Rn to M. Yes. So what I'm doing, this Ax, A is M cross N matrix. So, and this M is what? This A, N cross M cross N into N cross 1. So this was some X. Then X is going to this matrix actually. This is how it is defined. So X, N cross 1 matrix is going to M cross 1 matrix. So Rn and M, this M N cross 1 R is actually seen equivalent to Rn. Now is it clear? Rn, instead of considering it as a tuple, we are looking at it as a matrix, and this is new matrix which we are getting in M cross N. So this resultant is M cross 1 matrix. Is it clear now?
Whether A is the LA here, A is the linear transformation here.
A is a matrix using which we are defining the linear transformation. It is like Mm,
Are we telling this whole transformation process as LA? Yes. Actually,
yes,
from
yes.
X
The
n.
linear transformation is denoted by LA. And so, for example, if A is ABCD, then since we are in 2 cross 2 now, so LA, for this A, it is R2 to R2, such that any XY is going to what? This XY. Okay, matrix multiplication. And if I have this matrix B, E, F, G, H, then LB from R2 to R2 is what? XY going to E, F,
Can
G,
you
H.
R2 to R3? How
R2
it
to
will be
R3.
like?
So since we are going from R2 to R3, this will be a 3 cross 2 matrix. Okay, so it will be, so 3 cross 2 matrix means A, B, C, D, E, F. Okay, R2 to R3. So when I multiply this, A, B, C, D, E, F, X, Y. This is 3. This is 2 cross 1. This is 3 cross 2. Resultant matrix will be 3 cross 1 matrix. Is it okay?
So R3 should be always 3 cross 3. No?
R3 is R3. R3 is
Okay, that's all.
hmm.
Okay. Okay, thank you.
Hmm. Any doubts here? Any further doubts in the definition of LA? So this is the definition of rank of a matrix. So we work with this linear transformation and we know how to find range space, and then we can obtain from the range the dimension of that range space, and that is our rank of a linear transformation. So what here we do is we don't actually go and to find the rank of a matrix, we don't actually go and solve obtain its linear transformation and find its range and so on. We just use these two theorems or propositions which is already proved in the lectures, that let A be an M cross N matrix, then we have then B be an invertible M cross M and M cross M matrix, and C be an N cross N invertible matrix. So A, we are taking M cross N, B is M cross N, and C is N cross N matrix. Then we have this thing, that rank of A is rank of BA, rank of AC, rank BAC. Okay, so this is a proposition which is already proved, and this proposition we will use along with this proposition to conclude one thing, and that is what we will be using to obtain the rank of a matrix, B and M cross N matrix, in its row echelon form. Then rank of A is equal to the number of non-zero rows of A. So what we will do is, we have a matrix A. So using this, what I can do is, I have matrix A, and if it is in row echelon form, then number of non-zero rows actually gives me the rank of a matrix. So what I can do is, using this, so since A I can apply finitely many inverse row operations to get this to be some A dash which is in row echelon form, right? And once I have this, I can use this first proposition, which will prove what? That rank of A will be equal to rank of E1 to sorry, ek2 e1a, which is rank of this a dash. And for this a dash, rank is just number of, which is number of non-zero rows, because this a dash is in row echelon form as already given. So you're understanding what we are doing. It's not by default that just obtain a row, apply row operations, get a matrix in a row echelon form. In the background, when we actually find a rank by applying row transformation and counting the number of non-zero rows, these two propositions are playing the role in the background. We are actually using them explicitly when we do that. So what we will do is we will start with the A, convert it to the row echelon form by using row operations, and whatever the number of non-zero rows it has, this resultant matrix has same rank equal to this because of this first proposition which I wrote here. Because these elementary matrices are invertible matrices, and this B and C's here are actually invertible matrices. So elementary matrices are invertible. That is also a fact which we are using here. So let me start directly by obtaining, this will be more helpful, I guess. 22 by 7, 10011. Okay. And so I will do my first row operation. So E1 is R1 going to 1 by pi R1. So I'm just writing resultant matrix here in terms of, so E1A is equal to 1 by pi 0, 22 by 7. So second and third rows are remaining as it is, as I'm multiplying by 1 by pi only to the first row. Now my E2 is, I want to make this 22 by 7 0, because in row echelon form, once I have non-zero entry, it should be 1. And then every entry below that 1 must be 0. So I have 1 here, non-zero entry, which was pi. So I wanted to make it 1. So what I did, I multiplied by 1 by pi to the entire row. Now I have to make every entry below that 1 to be 0. So that's what I will do. I will do this R2 going to, when I say R2 going to, I am replacing R2 by R2 plus minus 7 by 22 R. So this is now the matrix E2 E1A, which is 1 by pi 0, 0, 1 minus this 27 by 22 pi, 0 and 0, 0, 1. Okay, and whatever this number is, I will just multiply this. Here it was 1. E3 is R2 going to this number 1 minus 7 by 22 inverse. This was R1, I guess. Then this E3, E2, E1A is 1 by pi 0, 0, 1, 0, 0, 1, 1. Okay, and now E4 is just, what I will do is R3 going to R3 minus R2, and this is E4, E3, E2, E1A, 1 by 2, 0, 0, 1, 0, 0, 0, 1. Is it okay? And now just, it was 1 by pi. And the last thing to do is R4, R1 going to, I will just subtract R1 minus 1 by pi R2. And this matrix E3, E1, E2, E1A is my now identity matrix. And it has 3 non-zero rows, right? This is in row echelon form and it has 3 non-zero rows. So therefore, in fact, matrix here itself was in row echelon form. Okay. So rank of so let me just write this also. E4, E3, E2, E1, A is equal to rank of E5, E4, E3, E2, E1 is equal to rank of A. Okay, by earlier proposition. And note that here, let me write his row echelon form. So even if we skip the fifth operation, we are still through because this is in row echelon form with three three non-zero rows. In fact, here also we are already in row echelon form. Okay, because no, this is not, because this is leading one, but below this is non-zero. So this is not a row echelon form. So please note, so check that this is not row echelon form, this is not row echelon form, but this is row echelon form. Okay, I hope what I'm doing is clear to you. So which is 3, because it has 3 non-zero number of rows. Any doubts here, please ask what I just did. Is it clear? I just applied row operation to obtain a row echelon matrix or matrix in a row echelon form. So even if I had stopped here, this is row echelon matrix, because one starting everything below it is 0. This is also non-zero 1 in second row. Everything below that second row is second 0 is 0, and similarly the rank of a matrix is equal to the number of its non-zero columns. Yes, that is also true, but if you are applying that definition, that rank of a matrix is equal to number of its non-zero columns, then you have to have the matrix in its column echelon form. Okay, so have the matrix in its column echelon form, then you can conclude the rank of a matrix is equal to number of non-zero columns. But if you are making a matrix in converting a matrix to its row echelon form, then number of non-zero rows will give you number of non-zero rows will give you the rank of a matrix. So note that is the thing. If you convert the matrix to its row echelon form and then calculate its column, then that might create problem. Is it okay? Because for example, if I have this matrix 1 0 0 0 1 0 1 2 3 1 0 0 0 0 0. So this matrix has rank 2. Okay, because row echelon form and 2 non-zero rows. Okay, so rank of A is 2. But if you count columns, number of non-zero columns, number of non-zero columns is 3. But that is not rank of this matrix. Is it clear? What I'm trying to say, that if you want to calculate columns, number of non-zero columns, you have to convert the matrix in its column echelon form. Then you can go ahead and calculate the count the number of non-zero columns. But if you are converting matrix to its row echelon form, you have to calculate the number of rows or count the number of non-zero rows. Is it clear? Don't interchange. If you are converting it into the one form, count those forms. I mean, if you are converting into the row echelon form, count the rows. Column echelon form, count the columns. Okay, so I hope that is clear. I mean, I don't think there was any doubts. Just convert the matrix to one of the favorite form which you like, and you can just apply that and count the number of rows. So I will move ahead to the next. So if you are asked to calculate rank of a matrix, just do this. Make sure you are applying valid row or column operations to obtain the row or column echelon form. Okay, so we'll move to the next question. So here, did I write? So rank of, let me just write here for, so rank A is equal to 3. That's it. Let me start with the next question. If you have doubt, please ask. Meanwhile, I will just write next question. A, B, and M, N cross M matrix. Let P and Q be invertible M cross M and N cross N matrices respectively. Then check the following statements are true or not. So we have to start with first question. They are asking that rank of QA is equal to rank of A. And what is your guess? Q is invertible matrix. So they are asking whether rank of QA is equal to rank of A or not. Any guesses? Observe that we wrote this statement here just now, just a few minutes back, which was giving us information about how the rank behave when we multiply a matrix by some invertible matrix. So we can just use this proposition actually. And Q is now this C here, which, or not C, but B here, which was playing a role of an invertible matrix, is our Q. Yes, as Sania said, that this will be true. So this statement is true just by this proposition. Similarly, I will go write the second statement, which is saying that rank of PA, oh, it's not QA, it's AQ. A is M cross N and Q is, wait. A is N cross M or M cross, okay, then A is N cross M, Q is, so I was correct then, it is QA. Then this will be AP is equal to rank of A, and as again we will use the same statement, and this is true by above proposition. Third one is rank of, I don't know whether I'm messing with the order of these matrices, but rank of APK. Please check the order of A, P, and Q, and accordingly, these APQs must make sense. So true again by above propositions. Proposition. So these three things are okay. So when I pre-multiply a matrix by invertible matrix, or post multiply it, or just multiply the matrix with the invertible matrices, its rank does not change. Okay, that's the significance of this proposition, and that's what this question is also asking. Now the final question, I would say question for this QAP. It will be QAP. Okay. Thank you. Thank you. It will be minimum of N comma M. And any guesses for this? So this is something non-trivial and is not given in this proposition. So any guesses? whether this statement is true or not, that rank of A will be less than minimum of N and M. So A is N cross M, I guess. It is N cross M. So it is N cross M matrix. Any guesses? It is true. Okay, so as guessed by Jackie, this is true. So, but if it is true, we have to give an argument where, okay, many people are saying that this is true. Even Karthikeyan said that this is true. So we will not like full-fledgedly prove this, but we will see that why this is quite visible using this statement. So they are saying that if A is M cross N matrix of rank R, so all these proposition which I'm writing here are actually proved in the week 6 lectures. Okay, please go through them. Then after finitely many row operations, row and or columns operations, we get a matrix of type this IR. This is 0 R cross N minus R, 0 M minus R cross R, 0 M minus R cross N minus R. So this I is identity matrix, IR is identity matrix, identity R cross R matrix, and this 0 I comma I cross J is 0 matrix of order I cross J. Okay. So this is the statement given to us. Okay, so and this matrix, so if A is M cross N, this is M cross N. Okay, this matrix, the resultant matrix obtained by applying row operations is again M cross N matrix. Okay, so and they are saying that if R is a rank, let me just highlight this. If R is a rank, this R is equal to this R here. Okay, so if I have a matrix M, so our A was N cross M. If at all it has some rank R, then there is matrix, square matrix, in fact, which is accommodated here in this N cross M. So this R is something which is less than N, and this R is also less than M, right? Otherwise, won't be sitting, this IR won't be sitting inside this N cross M matrix, right? So what this means that R is less than equal to then minimum of this N and M, right? It is quite visible, in fact, from this theorem that this R has to be less than both of this matrix, both of this N and M. So for example, if I am to write this 2 cross 4 matrix, 4 cross 2 matrix, 1, 2, 3, 4, 7, 8, 100, 104. Okay, if this is my matrix, this is 4 cross 2. So if this is obtained by, if I do row operations, the resultant matrix will be either, they are saying that it will be, if the rank is 1, it will be this. And here it will be identity means 1 and rest are 0, 0, 0, 0, 0, 0. If it has rank 2, then it will be of this form, right? But it can never have rank 3 because then I can't have such kind of stuff here. This is absurd. So this R must be less than both this M and N here. I mean, can you understand this? Is there any doubt here, like why this is happening or why this is very obvious from this statement?
I have a
If
doubt. Like,
yes,
yeah,
yes,
if
sir.
a matrix n into n matrix has a
Mhm.
column of all zero elements, then what will be the rank? What will be its rank?
Sorry, sir, you are saying that a
A
matrix
matrix
has
n into n matrix with
Mhm.
a all zero column,
with 0 columns.
with one all zero column.
Okay.
So what will be its rank?
We can't directly say from just by given this information that it will have rank n-1 or something like that.
Okay. So same is the case with all zero also, isn't it? All zero
All
rows
zero,
also.
all zero matrix has rank 0 because it does not have
No,
any
a
non-zero
matrix
rows.
with all zero rows. Suppose one of its rows is all zero, then
Yeah,
its rank will be n minus one, isn't it?
but let me show you this thing, okay? Suppose this is entirely 0. What I do is 1, 2, 3, 4, 4, 8, 12, 16, 0, 0, 0, 1. And what is rank of this matrix?
It should be three, right?
No, it's not. It's not 3. If you, because first of all, this matrix is not in its row echelon form. Because I have this leading one and below that one, there is non-zero entry. So I first have to convert this into a row echelon form or obtain a matrix of row echelon form and then check what is the number of non-zero rows when I have the row echelon form of a matrix. So when I have to do, so I want to make this 4 to be 0 and when I do that, I will get 0, 0, 0 here. I will do R2 minus 4R1 and this is what I will get. This is 0, 0, 1 and this is 0, 0, 0, 0. And what is rank of this matrix? Rank of this A here is equal to rank of this A. So if this is A and this is my B, rank of A is equal to rank of B actually, because how we obtained B? B is just obtained by applying a row transformation R2 going to R2 minus 4R1. So by the proposition which I wrote about ABC matrices, this proposition in fact. Using this proposition, I get that rank of AB is equal to B, which is 2. And by your guess, just because I had one of the rows 0 here, I can't conclude that it is 3. Okay, just having one non-zero row doesn't make it, or maybe three non-zero rows, sorry, 2 0 rows. I can just produce a matrix with rank 1, even having 2 rows entirely 0. Is it okay now? I mean, is it understandable? Like just
Yes.
knowing that
Yes.
one of the row is 0 doesn't make the rank to be n minus 1. That's what I'm trying to make clear here.
Yeah.
Okay.
So just that if one row is all zero or one column is all zero, we cannot find out
No,
the
we
rank
cannot.
from that.
We cannot. We are not saying that. I mean, from the matrix, I have to convert it into the row echelon form. So what this theorem is saying that when I have a matrix of rank R, I can do sufficiently many suitable row operations on it, or I can multiply the matrix by suitable elementary row matrices, and I can get matrix of this form. Okay, that's what this is saying. Is it clear?
Yes, it's clear.
Okay, okay. Then I will just move to next question now. Question 7. Let A be a matrix. A is equal to 1 minus 3 2, 2 minus 1 minus 2, 5 1 minus 2. Okay, this A is given. We have to compute the following. First, they are asking to calculate the determinant of matrix A. So let me just write the determinant, the definition of determinant. Okay, so we can have we can calculate determinant of any square matrix, and this is how we do that. If let A be an n cross n matrix, then we pick any I, pick a row I. Okay, from those n rows, then determinant of A is summation j from 1 to n minus 1 power I plus j. Aij. So A, when I write this, it means that A is actually Aij, I comma j from 1 to n. Determinant of Aij tilde. So Aij tilde is what? Where Aij tilde is an n cross n minus 1 cross n minus 1 matrix obtained by removing ith row, so ith row and jth column of A. Okay, so this is what matrix, and it is called as minor of ijth minor of matrix A. Okay, so this is the definition of determinant. So instead of going the normal, when we do, then what we learned in our 10th or 12th standard to calculate the determinant of 3 cross 3 matrix, what we were doing is actually we were calculating the determinant by choosing the row to be 1, and the row, and what this is showing us that 1 is not any special. We can start with any row and calculate the determinant for the matrix. So just to get hold of this definition, we will calculate the row and we choose our I to be 2, and we'll calculate the determinant of this matrix. Let me just copy this matrix A. And the determinant of A now is, since my matrix A is now 3 cross 3 matrix, this summation will run from 1 to 3. Okay, so summation j from 1 to 3 minus 1 power I am choosing to be 2, so it is 2 plus j A. I again I have already chosen the I to be 2, and determinant of this A 2j tilde. So what this is? Minus 1 power 2 plus 1 A 2 1, determinant of this 2j means 2 1 entry I am removing. So now I am what doing? I am removing this, and the remaining matrix is this 3 minus 3 2 1 minus 2. Okay, this is my A21 tilde plus minus 1 power 2 plus 2 A22, determinant of, now I need to do this with 2 and 2. So I need to remove this black rows and columns, and I will get it is 1, 2, 5 minus 2 and plus minus 1 power 2 plus 3 a 2 3 determinant of now I will let me just choose this with respect to this, and again second row is removed, and it is now 1 minus 3 5 1, and we can clearly it is minus 1 power 3 which is minus 1 a21 is 2 into determinant of this is this is minus 6 minus 2 6 minus 2 is 4. Oh, let me write 4 here. This is minus 2 power minus 1 power 2 plus 2, so it is 1 a22 is minus 1, you can see here, and determinant of this matrix is minus 2 minus 10, so it is minus 12 plus minus 1 power 5, so which is minus 1 a23 is minus 2, and determinant of this matrix is 1 plus 15, so which is 16, and what I get from here it is minus 4 plus 12 plus 32, so it is minus 8, and which is 36. Okay, any doubts here how I calculated this determinant? I just applied this formula and got the determinant. If you have any doubts, please let me know. And now second thing which they have asked us to calculate is the rank of this matrix A. So what we learned earlier was we were converting the matrix to its row echelon form, and then calculating non-zero rows there, and then that was giving us the rank. But apart from that, we have one more theorem which is proved already in our lectures, that let A, B, and n cross n matrix, then A is invertible if and only if determinant of A is non-zero. Okay, this information is already given to us. Okay, and apart from this, recall that in the lecture it is proved that if A is n cross n invertible matrix, then LA is also invertible. LA is invertible. So this will imply what? That null space. So LA is now bijective. LA is invertible, then it is bijective. So null space of LA will be 0. And again by dimension theorem, rank of LA will be what? N minus nullity of LA, which will be, so null space of 0 is 0. And therefore nullity of LA is 0. So this will imply rank of LA is, since A is LA is from Rn to Rn, or dimension of V is n minus 0. So which is n. And we know that this is exactly its rank of A. So in case of invertible matrix, rank of A is n. And we already know that if a matrix, using this theorem, if a determinant is non-zero, then matrix is invertible. And if matrix is invertible, we know that rank of that matrix is n. So here determinant of A was 36, which is non-zero. Therefore, A is invertible, and therefore rank of A is 3, because our A was 3 cross 3 matrix. And LA was from R3 to R3. Any doubt? I mean, the reason why I could have just started with the row operation and ended up getting row echelon form and conclude that this is this matrix A has rank 3. But I wanted to make this clear that we can just use a few results which come handy. I mean, and which can just save our time if we are to find the rank of a matrix in exam. So just calculating determinant is, I guess, easier in at least 2 cross 2 and 3 cross 3 cases, where you can easily find the determinant and conclude whether the matrix is invertible or not. So any doubts here? Okay, it's clear. Okay, so just the last quick question, which I would like to do because such question might be asked in the exam. I know we are up over the time, but I still would like to do this. Matrix, I'm taking just small matrix. Let me take 0, 2, 2, 4. Okay. Then calculate the two-tooth entry of the matrix 4A inverse. So when they are writing 4A inverse, they are saying that I want to first calculate A inverse, then multiply that A with 4, and whatever entry is two-tooth entry there, I mean this entry, this last entry here, I have to calculate that. So how to do this? So understand that if A is invertible, as we already stated earlier, A is invertible, then A is E1, E2, so on up to EK, right?
Can
It is
you
product.
take another case because this one would be non-invertible, right?
This one would be, why this one would be non-invertible?
Determinant is 0.
No, it's not, right? It is 4 minus 4. 0 minus 4.
Oh, sorry, yeah.
Yeah. No problem. Okay, so this now E. So using this, I will also have that A inverse E1 inverse identity is into A is identity, and using this I can just write this, or identity will be A inverse. So what exactly it says that when I apply E1 to EK, these are look at them as elementary row operations. When I apply the operations I apply on A to get identity matrix, when I apply those same operations on identity matrix, I get A inverse. So that's what we will do. What we will do is we will start with the A on one side, 1, 2, 2, 4, and here identity matrix. Okay. Identity matrix 1, 0, 0, 1. And I will do row operations such that I will get this A. I want to convert this A to 1, and whatever result, and I will apply those same row operations on this identity matrix, and whatever resultant matrix I will get, that will be inverse of this matrix. Okay, so I will apply first that R1 I'm interchanging with R2, and this will give me 2, 4, 0, 2, and here it will be 0, 1, 1, 0. And now I will just multiply R1 by 1 by 2, 1 by 2, sorry, 1, 2, 0, 2, and here I'm multiplying this matrix by 1 by 2. Sorry, first row of this matrix by 1 by 2. So this will be 0 and like this. And similarly, if I'm to then I will multiply 1 by 2 to R2, then this will give me 1, 2, 0, 1, 0, 1 by 2, 1 by 2, 0. And now what I will do, R1 minus 2, R2. And it will give me 1, 0, 0, 1. And here R1 minus 2, R2. So here R1 minus, so 0 minus 2, R2 is minus 1. So minus 1, 1 by 2. Here 0 is, it was 0 here, so it won't change. And this. So this is my matrix, which is identity matrix. And this is my A inverse. Okay. So that's why, therefore, this was two-tooth entry. So 4 into this matrix A inverse. Oh, two-tooth entry. Two-tooth entry of 4A inverse is now 0 into 4 into 0, which is 0. Okay, is it clear now? Now, before going, I would like to show one more, mention one more thing here, that when I did this last operation, it was changing the first row and not the second row. Okay, the second row was settled by here. I had already got what is needed in the second row in the identity matrix. So if I want to just ask about the two-tooth entry, I could have just stopped at this stage and got the information of this two-tooth entry at this position of A inverse. I mean, I hope I'm making this clear, because whatever operations I will do now are doing changes to the first row of a matrix, and they are not changing the second row of my matrix. So if I'm asked to give me the to calculate the information of second, I mean, just to save the time in the exam, you can just stop at this position here and you can get the information of the 2 to 10 3. I hope I'm making that clear. Okay, but if I was asked the information about this first row, then I had to go till the end and then I have to obtain the same. But this is just a trick and one thing I wanted to mention so that you can save time in the exam if you are giving exam. And please understand that when we are applying the row operations, what are the changes they are making when we apply those operations and which rows they are changing when we apply certain row operation. Okay, any doubts, please let me know.
If we multiply all these elementary matrices in a particular order, the first statement, can you please go on the top? Yeah. Here,
Yes.
EK inverse, E1 inverse, whether that is a product or in between, or what does this mean?
Yes, it is product actually. It is product. It is also product, and it is also same as applying that to corresponding row operation to the previous matrix.
It's equivalent, right? If you are
yes, it is equivalent. Applying a row operation, so that is already, so if this is my this is elementary matrix, okay, when I apply to this any matrix, I already showed this, it will just switch this, you can multiply and check. So when any operation I do here, so it is equivalent to saying that R1 interchange R2, if I'm calling this A, in A is similar to E R1 interchange R2 A. The resultant matrix obtained by interchanging R1 R2 is equivalent to multiplying the corresponding elementary of matrix obtained by interchanging R1 and R2 in identity matrix. Is it clear?
yes.
Okay. And you can just do that. I mean, just so let me just do this. If I am doing this 2001 and doing this, the matrix will be, you can see that 2, and here 2A, here 2B, here C and D. So what I did was, this was elementary matrix obtained by multiplying first row by 2. And similarly, when I'm applying that 2, multiplying this, it is equivalent to saying that I'm multiplying by 2 in to the first row of A. Okay, so is it clear now, like how things are changing? So when I do a row operation on a matrix, is it equivalent to saying that I'm multiplying that matrix by a elementary row matrix. Is it clear now? Okay. Any further questions or doubt anywhere? Okay, no doubt, then we can start, and I think we can stop, and we will meet next week same at 3 p.m. on Saturday.